So I am Jag. I have been with Red Hat for 3.5 years now. I initially came in as the chief architect for Ansible engineering, and then have since moved into kind of guiding the portfolio level architecture for all of the management products at Red Hat. Prior to that, I was a consultant to major media firms in the DC area, doing Django web development at scale, so Washington Post, PBS, Gannett, National Geographic, some of those. And once upon a time, in a former lifetime, I was the senior systems administrator for the Free Software Foundation and the GNU Project. So if you have any fun questions about Richard Stallman, I'll be happy to answer those. But tonight we're going to talk about caching, and particularly caching in regard to web applications. Given my background, this will be through a lens of Django and Python, but I feel like a lot of the concepts are extractable to other languages and other frameworks. So let's get started. Congratulations, you did it. You have a website. It's live. Good for you. Congratulations, everybody. Yes, give yourself a round of applause. You have a website. Good for you. And Neil Patrick Harris approves. Well done. But now your problems begin. People notice your website. People come to your website. People flood your website with traffic. All of a sudden, your website gets slower. You don't know what to do with all these people who want to come and use your website. And so now you have all kinds of problems. So you can add more hardware. You can scale out horizontally, and in most architectures that will work. But it is expensive. If you like things that are fully managed platforms as a service, like Heroku, scaling out horizontally gets really expensive really fast. Performance L dynos, those are the big ones, $500 a month each. Premium for PostgreSQL, that's the fast PostgreSQL with redundancy built in, $1,200 a month per replica. So yeah, all right, so you're a little more budget conscious. Let's do Amazon. We'll do all the management ourselves. Well, Amazon is also kind of pricey. M4 XL EC2 right now in US East 1 sits at about $145 a month per instance. And oh yeah, you need a database. So multi-AZ RDS, $540 a month. So this scaling out horizontally, you can do it. It's just going to cost you a lot of money. So in the Django world in which I come from, we talk a lot about premature optimization, that you shouldn't go out the gate trying to solve problems you don't have yet, when your biggest problem right now is, I don't have a website that anybody can actually get to and do anything with. Solve that problem first, then solve your other problems. Well, now you have a website. Now you have traffic. Now you have problems. And now is the time to start solving them. So the alternate title of this talk is Gimme the Cache. So we're going to talk about how cache can help you accelerate delivery of service to individual users without adding to your underlying bill at a linear rate. So the basic concept. Caching is a technical term for being lazy. We do this a lot in programming. This computer science is the science of laziness. We reuse libraries, we reuse methods, we reuse templates. We spend all day copying and pasting from Stack Overflow. A good day is a day where I haven't written a single line of code that somebody else hasn't written before me. We're lazy. If we don't let our servers be just as lazy, then we're hypocrites. And nobody likes hypocrites. Don't be a hypocrite. Let your servers be lazy. And that's what caching is letting your servers be lazy. So the basic concept, man, this is an older day. Somewhere in a basement in Virginia, some AWS UX designer is really, really proud of the icons they've come up with for all the AWS services. Like wow, this is so intuitive. Obviously, that thing in the middle is an EC2 server. I don't. Bear with me. So you got an ELB over there on the left, so a load balancer on the left that's splitting traffic among multiple EC2 servers. That red thing up there is your S3, so that's your object store for all your static content. Back there, that blue blob is your database, your RDS instance, and all of this is running in your virtual private cloud. Standard out the gate setup using Amazon. Well, cache isn't that much more complicated. We just add a couple more pieces. So over there on the left, the new red blocky thing, that's a CloudFront. That's a content distribution network. And then back here, that other blue blocky thing, that's your Elasticache. So that would be memcache or redis. So on the front, we've got a CDN like CloudFront. On the back, we've got some kind of cache service like memcache or redis. Adding these components is the first step to building caching into your applications. Now, for this talk, we're going to use the following terminology. I mean, not everybody agrees with this. And in fact, in the history of Django, they even switched which one meant which at some point in history. So for the purpose of this talk, memcache and redis are examples of upstream cache. And CloudFront and other CDNs are examples of downstream cache. So sometimes you'll hear them reversed, but when I'm talking about them, the key is that upstream is away from the client and downstream is toward the client. So let's remember that as we're going through and talking through this. Okay, upstream cache. So upstream cache, the redis, the memcache, it saves the results of expensive calculations that we frequently made so that we don't have to do them again, so that we can be lazy. Now, this is different than denormalization. If you have any kind of a formal computer science background, you know about data models that are fully normalized. We can denormalize databases. This is not the same thing. Cache is meant to be ephemeral. Whereas a database has persistence, has durability, cache is meant to be burnable. So it's not quite the same thing. So you cache a value for a fixed lifetime with a tolerance for a willingness to accept stale values. Invalidate cache values when saving updated values of the inputs that went into it. So we have, so the cache has a fixed lifetime where we're like, we're not going to cache this again. We accept the result is going to be old, but it's new enough. Or every time we know that we've made a change that's going to require that cache value be updated, we invalidate it so that it's no longer used once we know that it's no longer the case. Now, caching, there's lots of ways to do it, but I'm going to talk about some broad strokes for upstream caching. What are some good ideas? What are some bad ideas? And what are some things you might want to keep an eye on as you do it? So let's start with good ideas. Great ideas. All right. Properties. If you are a Python person, a property is a method on a class that looks and acts like an attribute. So it's a calculated attribute. Properties are great things to cache because they're the kind of thing that we're going to access once. We don't have to worry about arguments. There are no arguments to it. It's a calculated attribute of an object. That's usually that's a good place to look for things to cache. Complicated things, or compiled things, so like templates. If I'm in Python, I might use a Jinja2 template. Somehow I've got to get from this Jinja2 markup into some Python objects that I'm going to compile and then apply a context to. Well, that compilation step can take some computation. If we can serialize the Python objects and cache them, we don't have to recompile them again. Compiled things make for good cacheable values. Generated things, so things where we had an input and we created a derived output. So thumbnails are a classic example of generated data. Generated data is awesome for caching because the underlying input doesn't change, none of the derived values are going to change. And aggregated things. So if we're counting things, if we're looking for the maximum of things, if we're looking for the average of things, if we're looking for any kind of aggregated function across a set of data, these are usually computationally expensive things. And if we can deal with a bit of staleness for a while, you can save a lot of computational overhead by caching aggregated things. Okay, those were good ideas. Bad ideas. All right, things that I would not be caching. Rarely accessed things. Well, the idea of caching is you ask the question once. When you ask again, you save a whole bunch of time and computation. If you don't really ever ask again, you're wasting cache space, you're wasting the operations and doing the caching, not really anything where you're going to see any savings. Highly volatile things. So we talked about how you could either cache things and accept a certain amount of staleness, or every time the underlying thing that would make the cache value changed, you'd have to invalidate it. Well, if something's changing all the time and we need it to be reasonably fresh, there's not going to be a lot of benefit in caching it. So if it's a highly volatile thing, probably not a good idea to cache it. Things you need to be there the next time you look. So like we said, cache is ephemeral. You should be able to set your caching server on fire, and nothing about your website should change except that it slows down. So if you need it to be there, you put it in the database. You don't put it in the cache. The cache is where you put things that you don't mind throwing away. And things you should denormalize instead. So denormalization, when we create a derived value and we put it in our database, not only do we get the durability there, but we also get access to it when we're using that for other queries. So if we want to do a query that constrains on an aggregated value, denormalizing that so we don't have to go to our cache and get the aggregated value or figure out which aggregated value to get is a good thing to do. We can leverage the query planner in our database to take advantage of that aggregated thing in a query constraint. Yes?
Is what happens to floating point numbers that are so close to zero that for the smallest possible exponent, the high bit is zero.
Okay. So
what does that have to do with what you're doing?
Nothing. So in a fully normalized data model in a database, you have a copy of every bit of data once and only once. There is no duplication of data. If you have a one-to-many thing, all the things that are many are only stored in the many table. Denormalized databases are ones where different tables might have copies or aggregated values from elsewhere in the database stored along with it. So for example, if you have an organization that has a whole bunch of users that are associated with it, and you create a column on the organization table for number of users, and you update it every time you add a user record, that's a denormalized field. Or if you have the primary key from a related field, so if you have a many to one and then a many to one, and you store the primary key for this one here as well as here, so you don't have to do a join in order to access them, that again is a denormalization of your database. So a fully normalized model has a copy of every bit of data once and doesn't store any aggregated values that are then later updated. But a denormalized database has one or more instances of copies or aggregation across the models. Does that make sense?
Yeah.
Okay, cool. So if you are storing denormalized values to use in your queries so that you can constrain on those denormalized values, database is a good place to put those, cache is a less good place to put those. And then there's some things that might be good, might be bad, but be careful. So ORM objects. So in lots of different frameworks, we have objects which represent database rows. So let's say I do a query for a record, and I have the record, and I throw it in my cache. Then I come back 5 minutes later, and I pull it out of my cache, and I modify one field on it and hit save. Well, if another user has modified that record in the database during that 5-minute time, I've just stomped on their changes. So storing ORM objects in a cache can be good if you're willing to accept the staleness and you treat them as read-only. But you don't want to store ORM objects as your source of truth for things. You want to go to the database every time to make sure you're not stomping on any other changes. User-specific things. Oh, this is a great way to leak data across users. So if you have data which is user-specific that you throw in a cache, and then another user comes and you pull that value out of the cache, congratulations, you've just bled data across users. So storing user-specific things, you need to be particularly careful that while you can cache them per user, you also have to retrieve them per user. And you can't store them in a way where one user might get the value that was calculated for another. Even more importantly, admin-only things. So there are all kinds of times where you might have a template block that was conditioned on being an admin, and you cache that along with the fully compiled template. Well, you've just exposed part of your administrative interface and possibly some administrative data to a non-administrative user. So if you have things that require special privileges in order to be able to see, you also have to be very careful when throwing those in a cache, not to make sure that you do not show that information to a user who is not privileged to see them. So for those things, those last two, being able to store them in such a way that you reduce the risk of bleeding, how you organize your cache key namespace can help a lot. I think that every project should have its own cache key naming rubric. And a good one has a hierarchy. So let's take the example of where you're storing a particular cached value per user. Having the value and then the user identifier as part of the cache key is one great way to make sure you don't leak the data across users. If the key is composed from the user ID, that's much harder to do. What it also does is it allows for some cache backends like, say, Redis, you can scan your key space using glob expressions. So if you have a nice hierarchy, you can look and grab all the keys that match a certain pattern. But more importantly, it reduces the risk of collision, especially if you have multiple developers working on the same code base and there's no hierarchy whatsoever, no rubric for how we compose cache key names. You might have two different developers in two totally separate parts of the code base choosing the same cache key that have entirely unrelated values with them. So a good naming rubric helps people work together in the same code base with caching. The cache key should probably also contain all the pertinent values on which that key pivots. When we're talking about user-specific data, when we're talking about permission-specific data or role-specific data, putting the user ID or the role or the permission in the cache key helps us make sure that we do not bleed data, that we store different copies for different persona who are allowed to see different versions of this data. And it's also important to choose a delimiter that's probably not going to appear in any of those things that you're pivoting on. So for example, hyphen would not be a great delimiter for creating hierarchy in your keys. There's all kinds of different names that would probably include a hyphen, and now we're introducing ambiguity. We don't want ambiguity, we want clarity in our key naming rubric. So I happen to use double colon. It's just one that's easy for me, but lots of different ones you could use. You could use pipe. You could use backtick. You could use all kinds of things that are uncommon characters to see in a key name that a programmer might introduce in order to make sure that you are separating those things out for globbing and for avoiding ambiguity in your key namespace. Okay, so let's talk about.
Can you back up
Oh,
one
yeah.
to cover, again, all pertinent values in which the key pivots?
Sure, totally. So let's say, for example, I want to cache the number of emails this particular user has in their inbox, because that's aggregation is an expensive operation, especially in something like Postgres. Counting is really hard. So we want to store that count so we can reuse it in the future. Well, but we need to do that per user. So if we just have inbox count as our cache key, we're going to, lots of different users using the system, we're going to keep overriding that data with different users' inbox counts. But if our key is inbox count : 13528, where that's the user ID, then we will have a separate key for every user, and we're pivoting all the different inbox counts that we're storing based on the user ID. So the key contains all of the pertinent values where we're pivoting to make sure that we create unique keys for each of the different users. Or if we're doing this based on roles, so let's say there's some kind of a service catalog and you've got a requester and an approver, and those are different roles, but we want to do caching of things differently based on those roles. Putting the role name in the cache key, make sure that we can do that separately. Does that make sense? Okay, cool. Okay, so let's talk about different caching systems. Let's start with the file system. You might think, what? The file system? Yes, the file system. The file system is a fantastic way to cache your data. So why is it a fantastic way to cache your data? First of all, the file system is a great cache for large values. And when I say large, I mean entire dozens of kilobytes. So if you are storing things that have large values, the file system is a good place to think about storing them. Why? Well, first of all, or examples. So thumbnails and generated images. So if I am generating different scaled copies of a particular image asset, I don't want to throw that in a database. I don't want to throw that in memcache. I want to put that in the file system, because the file system is where you store files. And it's really good at storing files. Basically, anything you might download from another web service. So if you're downloading a JSON file or some sort of data file that you're using as input to any operation, you need to save a copy of it. If it's a file, store it in the file system. And we get all kinds of advantages there. So the paths themselves create an excellent key hierarchy. So if we're doing images, let's say we want to store thumbnails of images, we might SHA-1 the contents of the image file, of the source image file, and then create a directory hierarchy based on the first byte and the second byte and the third byte in order to make a nice tree in order to organize all these things. Second, the kernel. The Linux kernel does really, really smart things with files. So the Linux kernel aims to use as much memory as is available in the box all the time. If the Linux kernel aims to have zero free memory. Free memory is useless. But what memory isn't being used by applications, the kernel uses to cache pages off the disk. Because if it's in the memory, it doesn't have to go back to disk to get them, and memory is way faster than disk. So if you are reading files off disk and you read the same file off disk over and over, the kernel does not go to the disk to get it again. The kernel keeps a copy in its page cache and just serves it to you straight out of memory. So we already get a built-in memcache of files off the disk for the most recently accessed files. Additionally, the file system gives us all kinds of metadata about the things we store. When was it last accessed? When was it last modified? When was it created? Some very rudimentary locking. So we have the ability to have some fine-grained control over the data that we're storing in our file system. Basically, if you're caching a file, use the file system. Throwing it in memcache is a bad idea. We'll talk about why. Throwing it in a database is an inefficient idea. We'll talk about why. But yes, files go on the file system. OK, let's talk about, oh wait, oh yes, I forgot the added bonus. So there's the xsend file protocol. Raise your hand, you know the xsend file protocol? No, this is great. OK, so let's say I've got a standard two-tier system where I've got Apache sitting in front of a Python WSGI server, and it wants to serve a file off the file system. Well, so generally the way that that would work is, so when you read a file into Python to make the WSGI response, Python has to read and spool that file into memory. Python then has to send that content over a socket back to your web server. Your web server then has to send that content over a socket back to your client. That's a lot of copying. With xsend file, what we do is Python recognized, oh, hey, it's this file on disk that I want to be my response. Let's say it's this generated thumbnail that I want you to return. All it does is it sends an empty response with a special header x-send file with the path to the file that it wants to serve. Apache, being very smart, goes and grabs the file straight off disk just the same way it would any static file and serves it with all the efficiency of it. And so then it sends the content over the socket. So you save 2 copies in doing it this way. So Apache uses xsend file. Nginx has its own. I think it's XACCEL something or other. But these exist in our web servers. Using the file system as a cache for file content, you can take advantage of this. OK, let's talk about memcache. We all love memcache, right? Memcache is great. Memcache has its drawbacks. Let's talk about both. So the good stuff about memcache. It's a very simple key value store. You got a key, you got a value, all you need to know. The only things you can store, it's entirely ephemeral. There is no writing to disk, ever. If you restart the process, you just lost your whole cache. That's OK. It's a cache. We're supposed to be able to set fire to it. It's distributed and fault tolerant. You can have lots of different copies. You can bring them up and down, and you can still keep a warm cache across all of them. It's really well designed. It uses an ejection method from the key space called least recently used, LRU ejection. So when it runs out of space to cache stuff and it needs to kick something out in order to store something new, finds the thing you asked about the least recently and throws that out. So it's making sure to try to keep the newest things in cache versus keeping around stale things you might never ask for again. And you know, it's been around a long time. It's easy. It's super battle hardened. It's really fast. It's insanely fast. It's crazily fast because they cut some interesting corners. So memcache is great. But let's talk about those corners. They get faster because they are wasteful with memory, which is interesting. We'll talk about exactly how. This concept that they use in memcache called slabs. So we'll talk about how slabs waste memory. We have no ability to explore our key space. So we talked about globbing with our key hierarchies. Can't do that in memcache. You can't get a subset of your keys. You can list all the keys. You can get this one key. Maybe it's not there, but there's no real ability to explore your key space. Yes, no globbing. There's no data structures. It's just strings and integers. So you can store a string, you can store an integer, you can increment, you can decrement. That's the limit. So there are no lists, there are no dictionary hash kind of things, just strings and integers. Okay, so slabs. How is memcache so damn fast? It's because it cheats. Memcache breaks up the memory space into pages. By default, they're 1 meg in size. This is tunable. Memcache then chunks each 1 meg page into slabs, and slabs are also of a fixed size. So the slab sizes are enumerated. There are different ones that you configure at runtime, but they are configured at runtime. They cannot be changed while the process is running, only by restarting it. And each page, so each 1 meg segment, only uses 1 slab size. So you might have a 1K slab, so a 1 meg page with 1K blocks, a 1 meg page with 10K blocks, a 1 meg page with 100K blocks. Each 1 meg page uses only 1 slab size in it, so it's uniform across the megabyte. Okay, so this is a 1 meg page, and we've got 100K slabs. Okay, so 10 of them. That is 100 kilobytes right over there, the green. Cool. That is a 101 kilobyte string. Guess how many slabs it takes? 2. Wastes 99K of memory. Okay, that's an extreme example. But in general, so the upside is that fixed slab sizes allow memcache to make nearly all operations atomic, O of 1. Because all it has to do is know which page, it knows how big the slab is, it knows at what index in the slab, and it can jump immediately to that memory point and just start reading. So it's incredibly, it's a cheat that lets memcache get your data back out faster. But the larger the slab size, the more likely you'll be wasting memory and saving larger values. So I said storing thumbnails in memcache. Bad idea. So let's say we've got those 100K slab sizes. How often are your images exactly 100K? Everything in rounding up to 100K is memory that you are wasting. That can be 20%, 40%, 50% of your memcache memory allocation if you are not tuning your slab sizes to your data or storing things in there that are super wasteful. So big data does not belong in memcache. So let's talk about Redis. I love Redis. Redis also has its upsides and downsides. So Redis, unlike memcache, is a key object store. So it doesn't just store keys and values, it can actually store structured objects. Redis is single-threaded. There is no lock contention in Redis. You don't have to worry about concurrency control in Redis because only one client can do an operation at a time. Redis has one and only one thread. Redis can do transactions because a particular client can say, nope, I got this, and do a number of operations and then let go of the transaction lock, and Redis will not let any other client do anything in the interim. So Redis does have transactions for multi-step operations. Redis can persist to disk. You don't have to let it persist to disk, but it can. So restarting your cache means you're starting from a completely cold cache. Your performance will go down until your cache starts warming up. With Redis, you can snapshot state. And so when it comes back up after restarting, it is restarting from a partially warmed state. And Redis does have replication and HA failover. The automatic self-negotiating part of it is fairly new in the last couple of years. Prior to that, you needed something like a heartbeat in order to find out which one was alive, which one was dead. You could come up with a split brain situation. So it is there. It's a little bit of an art. Mm-hmm.
Does that preclude the possibility of using Redis?
No.
Because my understanding was with memcache clusters, you're dealing with multiple independent computes. Or does this mean in Redis it's going to reconcile it to one thread?
So I'm not familiar with the most recent feature set, but each server would have its own thread. And it could be a cluster that replicated, and so each one would be able to do operations at a time, but writes would be serialized.
Gotcha.
Okay, so Redis is great, but not so great. Because it's single-threaded, long operations block. So let's say there's an operation that takes 10 milliseconds. Doesn't sound like a lot, but if you've got a whole bunch of other threads trying to get into Redis, they can't do anything while that 10 millisecond thing is operating. The Redis documentation is really helpful in listing the complexity of every specific operation that you have in Redis. So O of n, O log 2 of n, O m log 2 of n. It's very clear about what things take more time than others. But I remember in one project I was working on, a developer had been caching lists to Redis and had a list with 100,000 elements in it cached to Redis, and did a record access at the very tail of it, which was a O of n operation. Took 11, 12 milliseconds, which is fast, but during those 11, 12 milliseconds, no other cache operation could happen. So long operations blocking on Redis can be bad and can slow you down in ways that you might not be able to predict unless you are aware of what you're stuffing into Redis and aware of what operations you're performing. Yes, out of memory. So whereas with memcache you say, I want you to use 100 megs of memory. Redis just keeps slurping down memory off the box. So Redis will return memory from the heap back to the kernel if it's at the end of the heap. But Redis doesn't defrag its heap at any point. So if you pull 100 megs of data in and then delete 99 megs of it, but it's the beginning and the end of that heap that are still there, Redis still uses 100 megs. So by and large, Redis's memory footprint during a runtime operation will only continue to grow. And so, yes, doesn't defrag the heap, not LRU. So you should expect that the cache set size you want to store is holdable in memory at all times. Generally speaking, the Redis memory footprint will continue to grow as it runs. So Redis can be configured to eject things when it runs out of memory on the box, or when it runs out of memory to a certain point. That's not its default configuration, but it also uses the LRU ejection method. So you can tune it to make sure you don't OOM, but out of the box it would OOM if it had the chance. Redis is absurdly fast. You can pull a M1 small and do tens of thousands of operations a second on Redis. It is really, really fast, but it's not as fast as memcache because of that slab searching. But key object means better data models. So we're not just limited to strings and integers. So you can have list operations for sequences. You can concatenate to a list, you can slice a list, you can chop off the last 10 elements of the list, you can grab the 43rd element of the list. You can do all these operations in Redis without having to pull out a string that represents a serialized JSON array and deserialize it and then do a list operation in your application. You can use set operations for collections. So Redis has lists, it has sets, it has dictionaries, hash maps. So for two-dimensional records, key values as values, Redis can do that. And it's got a unique data type called a scored set. It's a set where each element in the set is associated with a numeric score. I like to use these as epoch seconds for timestamps. It gives you a great way to say, throw away any record older than this, or I want only the records in the last 5 minutes. You can use the epoch seconds as your score, but that's another thing that Redis does have going for it. And its key space is glob searchable. So if you want to find all of the keys that match these first two parts of my key hierarchy, but everything after I want star, you can search Redis for all keys that match a certain pattern, which is particularly good if you're trying to do a wipe of a certain part of your key space without throwing out everything in your key space. Okay, cool. Upstream caching. That's our tour. We got it. You did it. Upstream caching took the load off your servers and your DB. You go with your bad self. All right, but you can tell how old this slide deck is by the vintage of this screenshot. So your pointy hair boss, oh yeah, pointy hair boss. I got Paige, what's up? Do you know what Reddit is? Why? Somebody said we made the front page and now our site is down. Are you ducking serious? I don't know, just fix it. We've all gotten something, well, it would be great if we got text like this all the time. So now we got to deal with downstream caching. So downstream caches store entire web responses and reserves them to future matching requests. So it doesn't require any computational cycles of any of our web infrastructure. To do this, we use a content distribution network. A CDN is a service with many exit nodes, geographically dispersed across the entire internet, so that users talk to the node that is closest to them in terms of the number of hops and latency. Downstream caches all obey headers that are stipulated in the HTTP RFC document, but they can be configured to override or ignore them. So there are standards that everybody kind of follows, but they don't have to listen. Okay, so HTTP specifies request and response headers that inform users as well as downstream caches. So these headers tell a CDN or the user's browser whether or not they're allowed to cache this particular document. Tells them how long this copy of the document should be considered fresh, so reserved again without going back to the origin service. And what to do when deciding whether or not to reuse a cache copy. So let's say I've got a copy of a web page and it said this is good for 5 minutes, but it's been 6. What do I do now? So as an example, and again, this will date this slideshow from timestamps here. I hope you'll forgive me. Okay, so we've got users, browser, Akamai, and our stack. So let's say the user goes and gets a web page off our site. The user makes a request to the CDN. The CDN first looks to see, do I have a fresh cached copy of foo.html? No. Brand new user, never seen it before, great. So the CDN makes the same request back to our stack, which we call the origin. So our service responds with 200, okay, but it includes 2 interesting headers. Last modified, which gives a ISO formatted timestamp of when this document was last modified, and then a header called cache control, which in this case says max age of 3600. Those are in seconds. So it tells the caching server, this was last modified on this date, but you can consider this to be fresh for 1 hour. So the cache stores a copy of the document and then returns the entire response just as it was received all the way back to the end user. Okay, so now a different user makes a request to the CDN for the same resource. Well, the CDN looks again to see if it has a cache copy, and lo and behold, it does. So CDN serves the fresh cached copy to the user. It's within the 1 hour window, everything's fresh. We didn't even see the request. It doesn't show up in our logs anywhere. Our infrastructure was not bothered with this particular request. It is just reused from the CDN. Okay, so an hour passes. So we're at 61 minutes. So our max age has elapsed. So another user requests the resource in question from the CDN. So the CDN looks and says, I've got a copy, but it's stale. All right, so it's got to go back to the origin. So what it asks is get that request, but it adds a header if modified since, and it presents the ISO formatted timestamp that the initial response said this document last changed on this timestamp. So the origin considers whether or not the actual document has changed since that timestamp. If we're serving a static file on disk, this is very easy. Look at the M time on the file. Has it changed since that? Let's say it has not. So it doesn't need to send the page again. If it's an application server, it doesn't need to generate the page again. all it replies is with an empty response of 304, not modified. In which case the CDN again considers the copy it has fresh, and so it serves it back to the user. So while our application server was questioned, it didn't have to go through the full process of generating a page because it figured out, nope, nothing's changed. Okay, so, yes?
Did user 2 and 3 receive a last modified header? Or is it just user 1 and 4?
They all receive last modified because the browser can also decide whether or not it wants to reuse a cache copy. Or it's your company and you have a SQUID server governing all of the exit traffic you have, and that SQUID server caches it for you. So there can be lots of caches along the line, even including the user's browser. So they all receive the last modified. Okay, so last modified and if modified since, they allow the CDN and the origin to state 304 not modified. 200 is okay, but 304 is better. So alternatively, so I'm doing this with timestamps. The origin server can also, in addition to last modified, give a header of e tag, which is just a hash. The corresponding header in the request will be if none match. So you can return a last modified and an e tag, and origin can respond with if modified since or if none match. And both of them do the same thing, just one of them does it on timestamp, the other does it on the hash of the content value. Now that cache control header, though, has a lot of options. We saw max age equals 3600, but there's a lot more that you can include in that guy. So max age is the number of seconds that the response can be considered fresh. No cache. The page must be revalidated with the origin before being reserved. Who thought that no cache meant don't cache this? That's not what it means. It means you can cache this, but you can't reserve it without revalidating it. Which sounds a little weird. No store. The page must not be stored in the cache, period. Okay, that's the one that you were looking for. Private. That also doesn't mean don't store this in a cache. This means that it's intended for a single user, so the user's browser can store a cached copy, but the CDN cannot. So only store this in a private cache, not in a public cache. Must revalidate. So this, you might think, because we saw no cache turned out to mean you must revalidate it, then what does must revalidate mean? So must revalidate is that the CDN must revalidate the page with the origin only after the cache copy is stale. So the CDN is not allowed to serve a stale copy without revalidating. CDNs can, like I said, can be tuned to have their own and override max age. This is just a little more forceful no. So it's all a negotiation. And then there's S max age, which is the same as max age, but it only applies to shared caches like CDNs. It doesn't apply to browsers. So you can give in a response, your user, your browser can store this for an hour, but any shared cache should only store this for a minute. So you can do those separately. Additionally, you can instruct a CDN to store different copies of the same page on the URL, the same way that we did pivoting the key namespace for an upstream cache. The downstream cache, you can do the same thing, but varying on HTTP headers in the request. So common ones you'll see are vary except encoding. So let's say you have one user who only accepts UTF-8 and another one who's in Asia and accepts Big 5. Just because it's the same URL doesn't mean the application server would serve the page back in the same encoding. So this tells the shared cache you can store a UTF-8 version and a Latin 1 version and a Big 5 version and store them pivoting on the request header of accept encoding. Cookie is another common one that you'll see, which is a lot of folks will use as a hack in order to try to store different cache copies per user, particularly if you're, you have a session ID or something, so you'd not let the cache would not bleed copies between users, but in practice this doesn't work because advertising and analytics embedded in most commercial web pages also save cookies, and literally every time the whole cookie string changes, you get a new copy in your shared cache. So if you use like Google Analytics, which sets a cookie for every single request, you're not getting any advantage from your downstream cache that way, because the cookie value will continue to change over and over. You can't vary on just one particular cookie value. It's the whole cookie string. And again, I'm a Django guy, so caching headers in Django. So Django employs two cache middlewares. If you think of a request as an onion and you're firing a bullet through it, on the way in, you have Django request middlewares. On the way out, you have Django response middlewares, but they're in inverse order. So the first request middleware is the last response middleware. It's like layers of an onion. So it has fetch and store. So fetch is the fetch checks to see if it has a copy of this page already cached. Store stores a copy for retrieval later. This is all configured in settings.py. You can tweak those settings on a per view. So there's decorators you can use to say, this view, I want you to set a max age of 60 seconds, whereas my default is 1 hour. So you have a lot of ability to tweak this. Just remember that if you do touch request.session in a Django view, it updates, it sets very cookie. So anytime you touch Django tries to make sure that you can't do that user bleeding thing, where you cache something for one user and then serve it to another. So if you do anything to touch request.session, which means asking request.user or looking at a particular session value, then Django is going to include in the response very cookie just to make sure you don't accidentally store multi-user things. So just be aware of that. Say again?
It also prevents session.
Yes.
Yep.
Yep. Yep. So Django is really great at making, putting the styrofoam things in the corners of the table so we don't bonk our head. Like it's really good at making sure it's hard to do something dangerous. You can also in Django out of the box use e-tags. So basically what happens is when it generates a response, it runs it through MD5 and calls that the e-tag. The thing is that Django has to go and recalculate the entire view in order to figure out what that MD5 is. So it's built in if none match still runs the entire view. It just doesn't have to transfer it. So you get a bandwidth savings, but not a computational savings. So the real takeaway here, though, is try to 304 efficiently. So if you can quickly answer 304 not modified with less processing, do it. This is a good way to integrate upstream and downstream caches. So if you have modification timestamps on objects, so let's say I'm going to a view that's a detail page for a particular object, and I have a timestamp on that object in my database for when it was last updated. It's super easy to just go and grab that thing first thing if there's a if modified since header in, and check to see if the object itself is modified. If the object hasn't modified, the response probably hasn't either. Don't forget to check for the last code release, though. So you can check to see if the objects have modified, but you also ought to probably store the timestamp of your last git commit for this release so that if you've updated your templates, if you've updated your views, even if the database objects haven't changed, you're not serving stale content. You want to make sure that you're serving all new content when you do a new code release. Balance the max age, S-max age with the volatility of the data and the needs for your site. So you can get a lot of savings by caching for longer, but you're going to be serving a lot of stale data. You can make sure you have a lot fresher data with much shorter max ages, but you're going to be involving a whole lot more compute. So understanding your business needs, understanding the volatility of your own data set, you can tune max age and S-max age to the needs of your site. The other thing that tends to mess up the 304 efficiency is user-specific content. So if different content is being served per user, the utility of a CDN goes down sharply. It would only reserve the same page for the same user under the same conditions. You can do a little re-architecting to make that easier. So if you're using a template engine and serving rendered HTML with data from the back end, you can probably abstract out parts such that the general same for every user's content is the background, and then you load the dynamic user-specific parts using JavaScript, in which case you can serve that background totally cached, same for everybody, but load the user-specific parts dynamically. Yes, exactly that part. And this also works for related content. So if you're looking for, here's a particular article, but this content is recommended for this user, or here's this article from 2 years ago. This related content is going to update every time that we have new content published. You can cache the hell out of that article, but load the related content dynamically through JavaScript and XHR. So the parts that are volatile or the parts that are user-specific, you can load dynamically using JavaScript. But the parts that are constant and stay the same, you just template, cache, use aggressive downstream cache headers. So here's a project I did 4 years ago for the folks who run the MCAT. They're great people. So everything on this page, with the exception of one thing, is the same for literally every user who hits this page. That little bit up there is the only user-specific part of this entire page. So if we had generated this for every user and touched request session on our Django object, we would have lost all the benefits of all downstream caching, because we would have to generate a new page for every user that was logged in. If instead we serve the whole page and then do the little login thing dynamically, so use JavaScript to test to see if there's a cookie there, go out and grab a session object from using an XHR, come back and render that to see whether they're logged in or not, or hello JAG, click here to view your profile, click here to log out. That part is dynamic and loaded after the fact, but the entire page itself can be stored aggressively in our CDN. Does that make sense? Cool. Other CDN concerns. Not every user will actually hit your site. So counting lines in your access log no longer is a way that you can use to tell how many users you've had on your site, because not all of them will hit your site. So since access logs won't give you the complete picture, that's where client-side analytics come in. That's the value of something like Google Analytics. So no matter if the user is seeing a cached copy of the page that your app servers never saw or not, there's a JavaScript ping to an analytics service that gives you detailed information about the users hitting your site. Not all CDNs follow RFCs. So there are those headers, there are what they should mean, but different CDNs and different caching servers make up their own rules sometimes. As an example, Akamai completely ignores cache control private. So even though you give it a header that says, you may not store this, you are a shared cache, don't even store this under any circumstances, it still will. Maybe they fixed this, I don't know, but you should expect some idiosyncrasies from different CDNs. Purging from CDNs. So let's say you do a new release and you've done a bunch of changes to the look and feel. You want to clear that downstream cache so you don't serve any stale content. Well, it's got a lot of points of presence all over the internet, all serving this cache copy. Wiping it from all these different edge nodes, it takes some time. So you can't expect to necessarily just click delete this from across the entire internet. Some of them are faster at it than others. Akamai is like 15 minutes. Amazon's probably like 4 or 5. But it does take some time in order to propagate that request across the entire internet. So, okay, cool. We got both upstream and downstream. Try to stay humble. It's hard being this awesome and saving companies this much money. And yeah, so your boss will be happy when you cache, because your AWS bill will go down, your performance time will go up, and money will fall from the sky. Okay, so to recap, we use upstream cache to reduce expensive calculations. We should use the file system to cache things that really just actually are files. And when we do, we should use xsendfile, because that's a great way to improve efficiency. We should use memcache or redis for smaller and more ephemeral storage, but in choosing between the two, we should know the strengths and weaknesses of our cache engine, tune it to our hardware, tune it to our use cases, tune it to our needs. And make sure you define your key space intentionally so that you don't have different developers writing over each other's keys, and so you don't accidentally bleed information between users or between roles based on not including that pivoted value in the key. And yes, be careful what you cache. Make sure that what goes into what comes out of a cache is not going to have any kind of authorization test to it. So just make sure that what you're caching, you're careful about what you cache so you don't stomp on values, so you don't bleed data between users. And then use downstream caching to get pages to users' eyeballs and brain meats faster. So inspect and tune your HTTP caching headers. There's the developer tools in every major browser. You can look at all the request headers. You can look at all the response headers. You can play around with it and see exactly how your browser reacts to them. Optimize your views toward 304, when it's possible. For a lot of views, there's no way to really optimize toward that, but detail views especially, that's pretty easy to optimize toward. And where you can, if you're doing rendered templated content, try to abstract out the user-specific parts to load dynamically using JavaScript and XHR so that Chrome, that background, is much of the common for every user content that you generate, that you have. You can use the CDN more efficiently. And then finally, know the strengths, weaknesses, and peculiarities of your specific CDN provider. No doubt there are countless Stack Overflow articles on people who found out this weird non-compliance of their particular CDN. Okay, yes, shameless plug time. Come work with me. So I work for a little company called Red Hat. We're based out of Raleigh. It's now also available in blue. Red Hat was acquired by IBM. That deal closed this summer. But by and large, none of us have noticed. Red Hat is an independently operating subsidiary of IBM. So our CEO reports directly to their CEO.
So blue ties.
No, they're leaving us alone. So I think everybody's hope is that things in the Red Hat culture will begin to sift through osmosis into IBM. I look at the IBM deal. They spent $34 billion. They spent $2.5 million per employee. They gave a 33% premium on our stock price. They spent 1/3 of their market cap on buying us. For a company with no proprietary intellectual property, no trade secrets. The only thing we have going for us is our culture. And Red Hat's culture is easily the source of its persistent competitive advantage. IBM could have you can get the source code for every product Red Hat has, and you can make your own competing product for it. IBM could have done that for 1% of what they paid for Red Hat. So for what they spent, they're not buying us for our products. They're buying us for how we make them. So my expectation, the expectation that has been communicated, is that IBM wants to leave Red Hat alone as much as possible. We'll see. But Red Hat supports a lot of remote work culture. I work here in Asheville. There are, I think, 8 or 9 different Red Hatters around Asheville. One of the product managers I work closely with, he's here in Asheville. And so a lot of Red Hat's positions that are based out of Raleigh, based out of Boston, are doable from here in Asheville. So you can look at jobs.redhat.com if you're interested. You can reach out to me on Slack. I'll give you a special referrals link, which will say referred by Jag, and they all like me, so that'll give you a little leg up. But otherwise, that's me. You can find a little bit about me at my vanity URL, and if you live in the cesspool of Twitter, that's how you can find me right there. Thanks very much, y'all.
Thank you.
Well done.